It's really an honor to be here on this very special occasion to celebrate the historical solution which we heard about from Kerr himself yesterday. And I think the significance of this, the Kerr metric, is perhaps most eloquently summarized by the quote of Chandrasekhar that Bernard mentioned yesterday. That it's truly remarkable that a solution so simple, specified by just two parameters, actually describes so many black holes that we see exactly, and now which we are beginning to observe more and more closely. And so the take-home message from that, and we have heard many talks on this, is that a classical black hole is extremely simple. It's much simpler than the gravitational field around this table, for example. What I'm going to talk about is the complexity of black holes. So a black hole is at once the most simple and the most complex object, and understanding the simplicity is in the realm of classical gravity, which is what we have heard about mostly, and understanding the complexity is in the realm of quantum gravity. So the main difference between all the previous talks and mine is going to be that Planck's constant was set to 0, and in my talk Planck's constant is going to be set to 1. And I will not give you, but I would like to just give you a flavor of how one can actually make some progress in this highly theoretical field, following some very robust principles and just following what the equations are telling us. And a great deal of quantitative information about semi-classical and quantum properties of a black hole have been obtained entirely on the strength of theoretical considerations. And this makes for an interesting study in history of science. Just as in the case of even the classical black hole, people proceeded pretty much following Einstein's equations before much evidence was there for its actual existence. So the outline of my talk is that I will just very briefly remind you about classical black holes, semi-classical black holes, and then describe quantum black holes. And the main reason for somebody like me, or for many people working around this field, for being interested in quantum black holes, is that they provide us with an invaluable tool to learn about the short distance or the ultraviolet structure of quantum gravity by studying long distance or infrared properties. And I will explain what that means. So why is classical black hole so simple? We know that it's because of the no-hair theorem that a black hole is completely specified by its mass, spin, and charge, much like an elementary particle, like an electron, given by the space-time is given by the Kerr-Newman metric. And therefore, a black hole, unlike a star or a table, is extremely simple. And it has an event horizon, which is a one-way surface that causally separates the outside from the inside. So this is our understanding of the classical black hole. And what I want to do is that, many of you may have seen this before, but I just want you to run you through this logic of this inquiry to convince you that if you just follow the logic to its conclusion, you are led to some rather dramatic conclusions. So the first paradox, this raises a paradox, the existence of an event horizon, and the following paradox, which is the very simple-minded but incisive question asked by Bekenstein, that what happens if you throw a bucket of hot water into a black hole? Because then the entropy of the world outside the black hole would decrease and violate the second law of thermodynamics, which we believe to be a kind of a sacrosanct principle. And the resolution would be, he proposed, that a second law could be saved if the black hole also has entropy. Then the total entropy of the black hole and the bucket can increase, just like the black hole has mass, in accordance with the second law. But this leads to the second paradox, that if a black hole has entropy, as you want to save the second law, and mass, then by the first law of thermodynamics, it should also have temperature. But then it must radiate, which is impossible for a classical black hole, because the event horizon is a one-way surface, as we said. And the resolution is, of course, the celebrated discovery of Hawking, that because of quantum pair creation near the event horizon, a black hole can actually radiate, even though classically it cannot. And in this picture, the metric is treated classically, which is why it's a semi-classical analysis of the black hole. So the semi-classical black hole, the one main thing that we want to take away from it is that it has temperature and entropy. And as we know, this famous formula, the Bekenstein-Hawking formula, that the entropy is given by this beautifully universal formula, which depends only on the area and all the three fundamental constants of nature. It's a remarkably general formula, and therefore the black hole, because it has enormous entropy, it signifies a huge complexity. So even though the classical black hole started out being simple, the semi-classical black hole is extremely complex. And this raises the third paradox, that if a black hole has entropy, then in quantum theory you have to be able to interpret it as an ensemble of microstates according to Boltzmann. So how do we associate so many microstates with something which is just a hole in space-time? And to resolve this paradox, what we really need, we really have to face up to quantum gravity. We really need a well-defined quantum Hilbert space in which you can count and say that, okay, here is the count for the states and here is the black hole entropy. And this, I would say, is partially understood in string theory. It's far from being completely understood, but I think there is already remarkable progress in trying to understand this question. So therefore, we have to deal with quantum gravity. So what is, as we know, one of the enduring challenges of theoretical physics is to find a consistent framework for quantum gravity that unifies general theory of relativity with quantum mechanics. And we know that there are very serious problems having to do with the fact that Newton's constant is dimensionful. So if you apply standard rules of quantum field theory, you just get divergences. The theory is non-renormalizable, and you don't know how to make sense of the theory. And string theory in the starting offers a promising route towards such a quantum theory of gravity, and it has a few things going for it. First of all, it tells you how these non-renormalizable divergences can be controlled. So the theory is perturbatively ultraviolet finite. This was already known in the 80s and 70s. Then in the 90s, people discovered this remarkable strong weak dualities, such that some very strongly coupled string theory where quantum fluctuations are large has a dual description in terms of another weakly coupled theory. And now more recently, there is this, well, not so recently, in fact, already 15 years, the anti-de Sitter CFT holography, which I will briefly talk about later. So even though there are signs that string theory has the right ingredients, there are many problems. And the main hurdles for string theory is that, first of all, we don't have a microscope like the super LHC by which to probe the theory directly. Secondly, even worse problem, which many of you might have heard, is that we don't even know which phase or compactification of the theory might correspond to the real world. So it's a bit like knowing the Hamiltonian of, say, H2O, but you don't know whether you're in the water phase or in the vapor phase. And in which case, you cannot really make predictions because you don't know. And therefore, the question becomes then, how can we really be sure that string theory is the right approach to quantum gravity in the absence of direct experiments? And that's where actually the black holes and the wonderful properties of black holes that people have discovered come to help us. In such a situation, a good strategy when you're in this situation is to focus on universal features that should hold in all phases of the theory. So if something is true in the water phase as well as in the vapor phase, then we can check whether it is correct or not and conclude of whether our Hamiltonian about water is correct. And entropy of black hole is precisely one such quantity which gives us very precise quantitative thermodynamic information independent of which compactification you're talking about. And therefore, in a quantum gravity, it should be possible to interpret the black hole as an ensemble of state in any phase of the theory. If any phase of the theory admits a black hole, that you should be able to interpret it as an ensemble of states. And if you fail to do that, then you know that you can just forget about string theory. So this is a kind of a time-honored tradition in physics that in the absence of a microscope, one can often learn a lot about the microstructure purely from thermodynamic properties. For example, a condensed matter physicist, or in the early 20th century, just from the temperature dependence of specific heat of a metal, you could figure out whether phonons are responsible or electrons are responsible. And the quantum properties of black holes we would like to put to similar use. And it's good to keep a historical analogy in mind. For example, kinetic theory of gases was a triumph of the 19th century physics, which formed the basis for atomic hypothesis and later for quantum theory. So, for example, in this room, we all believe that there are nitrogen molecules, but we cannot really see them. So, how do we even be sure? And this, of course, we know that Maxwell's very simple theory of ideal gases, of kinetic theory, to explain the macroscopic properties of ideal gases in terms of some microscopic atoms was highly successful. And even though at that time there was no microscope at the time that could establish the reality. So, this is the kind of thing that we want to do, that basically if you want, you can measure the entropy of a dilute nitrogen gas by doing an experiment, and then you do a count, d of, this is the room, there are these nitrogen molecules. So, volume divided by the typical size cube is the number of boxes, and there are so many ways of putting these molecules there, and then you have to divide by this 1 upon n factorial. And what is amazing is that if you just use de Broglie wavelength of the nitrogen molecule, this agrees with experiment. So, this was one of the big successes of kinetic theory, and people have tried to use this reasoning, this kind of reasoning, in the context of black holes. So, this line of reasoning has already led to some advances in the 1990s in the context of black holes, that for a large class of special supersymmetric charged black holes, so these are more like Kerr-Newman black holes in some extremal limit, can be interpreted as ensembles of microstates as required by Boltzmann. Moreover, there are generalizations of the black hole, which is like a point object. You can have an object extended along a string or extended around a brane, which are called membranes, which occur very naturally in string theory. So, there are extended versions of black branes, and this has led to this very remarkable equivalence, holographic equivalence, between a theory of gravity in anti de Sitter space and a theory without gravity. This is called holography. This is already a very remarkable correspondence, and which people are only beginning to understand, and it should really surprise you, and it never ceases to surprise me that a theory in which things fall is supposed to be exactly quantum equivalent to a theory in which nothing falls. But most of this work was done mostly for large area black holes or large charged black holes. So, let us just push on, but before we go there, I just want to tell you an example of that. So, for example, this is the famous work of Strominger and Waffa in the mid-90s, that they showed that if you compute they took some special black holes, basically in 5 dimensions, a cousin of Kerr-Newman black hole, let us say, Kerr-Newman black hole. Instead of having just one Maxwell field, you have 3 different Maxwell fields that come in string theory, and therefore you have 3 different charges. So, you compute the area of this Kerr-Newman black hole divided by 4, and you find that it equals 2 pi square root of q1, q2, q3. And then because in string theory we actually have a quantum Hilbert space, you can go and count how many, just like we counted the number of ways oxygen or nitrogen molecules can fit in this room, you can actually do a counting, which is a completely different calculation in the Hilbert space of the theory, nothing to do with geometry. And remarkably, they found that for large charges up to this 2 pi, there was a very beautiful and precise agreement. Now, so our current understanding is that a black hole is simple not because it is like an elementary particle, but rather because it is like a thermodynamic ensemble. Because we know that thermodynamic ensemble is also specified by a few conserved quantities. And this explains why it is both simple and complex at the same time. Now, can we mine this very important piece of information further to get some clues about quantum gravity? So, that will be the subject of rest of my talk. So this was more the background. So now, therefore, I come to quantum black holes, that given such a beautiful but approximate agreement, approximate because we are considering large charges here, it is natural to ask in physics, whenever you get some formula, first of all, can you calculate corrections to it systematically? Are the corrections small? And what is the exact formula to which it is an approximation? So the question becomes, what is the quantum generalization of the Bekenstein, the famous Bekenstein-Hawking area formula for the entropy? Is there a quantum generalization? And if there is, how do we systematically go about computing it? Both these corrections, quantum corrections to the entropy, and then how do we compare it with some microscopic counting? And this actually took a while to really settle down. And the philosophy, again, to go back to our historical analogy, is the following, that by asking more subtle with more subtle statistical considerations, one can obtain more interesting information. I mean, for example, going back to the historical analogy, we know very well that in this our counting problem of nitrogen gas, we needed to put an n factorial because the nitrogen molecules are all identical. Now, Gibbs could deduce this very important fact about the microstructure by just demanding extensivity of the macroscopic entropy. And this was, 60 years or many years before the spin statistics theorem that you really require quantum field theory to prove it. Even more dramatic example of this is the classical equipartition theorem, as we know, is wrong, gives, for example, for specific heat of nitrogen, you get wrong answers if you apply classical thermodynamics, statistical mechanics, essentially because these vibrational degrees of freedom are frozen because of quantization at low temperature. And it's remarkable, I mean, if you just look at, just for historical curiosity, Maxwell, for example, understood way back in 1859 that this was the greatest difficulty facing classical molecular theory, even before we were actually sure about atoms and forget about quantum theory. And Jeans made a prescient remark that, well, it looks like the degrees of freedom are somehow frozen. But the point is that some of these far-seeing physicists were able to sort of diagnose a serious crisis of classical physics just from these very thermodynamic reasonings, and that's the kind of thing that one would like to emulate. So what is new is that much of the, as I said, much of the earlier work on black holes was, and holography, was for black holes with large area, and now I will move to these quantum corrections to this black hole entropy. So all those formulas were valid when the black hole was very large, when the area of the black hole horizon went to infinity. And what I want to now ask is that, can we compute the entropy of the black hole when the size is actually finite? And can we compute it in a reliable way? We'll take some simple system, but even for a simple system, can we do it? Now, unlike the leading Bekenstein-Hawking formula, why this is interesting, these finite size corrections, and why do we care about them, is that unlike the leading Bekenstein-Hawking formula is determined entirely by the Einstein-Hilbert action, because you know that all the area theorems and everything of classical general relativity follows once you're given the action, Einstein-Hilbert action. Whereas these finite size corrections actually depend on which details of the particular string theory compactification that you're looking at. So this gives you, this is why I call it a window into the UV structure, that it tells you something about the ultraviolet structure of the theory. So why obsess about black holes? So just to summarize, well, I mean, this transparency actually I wrote for a colloquium at CERN. So to a group of particle physicists, you really have to explain. Now here, everybody is obsessed about black holes. So I don't need to explain why we obsess about black holes. But why do we obsess about these quantum black holes? That, as I have said, that it's a very universal and extremely stringent constraint that in any phase of the theory that admits any black hole as a solution, it should be possible to view it as an ensemble of quantum states. And if you fail to do that, then your theory is just wrong, even without doing an experiment. And quantum entropy, as I will show, acts as an infrared window into the ultraviolet, in that from studying these finite size corrections, we can obtain very precise quantitative information about the ultraviolet structure of the theory. So what do we want to do? So as we said, this is the famous area formula where A naught is 1 upon 4, say for a large black hole. But we expect that the entropy of a black hole actually will have an expansion of this form, that the leading formula will be area upon 4, but there will be corrections like log of the area or 1 upon area square, or even exponentially small corrections like e to the minus a. So there will be perturbative corrections and non-perturbative corrections, and perturbative means perturbative in 1 upon a. Now there is already a generalization due to Wald, who generalized the Bekenstein-Hawking entropy formula to more general local actions, where instead of just Einstein-Hilbert action, you can have r squared term or r to the 4 term, because generically we expect that when you integrate out quantum fields, you generate typically higher order terms. So it's only at low energies we expect that only Einstein-Hilbert action is good only at low energies. So there should be a generalization, and that was proposed due to Wald, but that's applicable only for local actions. And in general, massless fields lead to non-local terms. So we need some generalization of the Bekenstein-Hawking-Wald formula that is truly quantum. And a proper definition became possible in 2008 for supersymmetric black holes again, using what is known as holography. So I will now very quickly explain to you what is holography. And so this, let's go back to our paradoxes. This is the paradox number 4. That if the entropy in of a black hole scales with area instead of the volume, then, and we also know that the formation of a black hole is a spontaneous process. So if I took a large enough room with some gas in it, it will spontaneously collapse to form a black hole, and therefore, according to the second law of thermodynamics, your entropy cannot decrease. And therefore, the initial entropy of the volume of space should also scale not with volume, but with the area. Now, this is a very bizarre statement, that you would expect that normally if you have some crystal in this, then the entropy would go, if you have some crystal separation, would go proportional to the volume of this room and not to the area of the walls of this room. But that's what black holes seem to tell us. And these were kind of heuristic considerations by many people, including Bekenstein and 't Hooft and Susskind, who concluded that d+1 dimensional theory of quantum gravity must have degrees of freedom of a d-dimensional theory, much like a holographic imprint of a 3D object onto a 2D hologram. So, are there any questions at this point? Now, this heuristic idea actually has been realized very concretely in string theory, which goes under the name of anti-de Sitter CFT correspondence due to Maldacena. And it's a truly remarkable quantum equivalence between a theory with gravity in anti-de Sitter space-time, in the string theory moving in anti-de Sitter space-time. Anti-de Sitter space-time is just a maximally symmetric space. It's the analog of a sphere, but maximally symmetric with a negative cosmological constant. And a theory without gravity, which is so this is called ADS, and the CFT is the conformal field theory in one less dimension. And the anti-de Sitter space has a boundary, and much like people imagine with the holographic principle, that this conformal field theory is somehow associated with the boundary. And Maldacena arrived at this by considering a near horizon limit of a p-dimensional brane. So in this language, a black hole is a zero brane. I mean, it's point particle. It's like a point-like object. You can have an extended object which is like a string, or a two-dimensional object which would be a 2-brane, 3-brane, and so on. And just like we are familiar, everybody in this room is familiar with the fact that the near horizon geometry of an extremal charged non-spinning Kerr-Newman black hole, otherwise known as Reisner-Nordstrom black hole, is anti-de Sitter space 2 times a sphere. So, four-dimensional, if you take a four-dimensional Reisner-Nordstrom black hole and you take the extremal limit, then the near horizon space-time is anti-de Sitter 2 times S2. And there is a generalization of that to when there is a membrane, if there is a string, then it's an ADS3, anti-de Sitter 3 cross S2, and so on. If you have 4 brane, then it is 3 brane, then it is anti-de Sitter 5. And then you might ask, how can, for example, the most well known of these is the ADS5 CFT correspondence, where the CFT is some 4-dimensional gauge theory, quantum gauge theory, like QCD, and ADS5 is some anti-de Sitter 5-dimensional anti-de Sitter space. And you might ask, where does this extra dimension come from? And it comes from the renormalization scale of the conformal field theory, of the quantum field theory. It basically takes the form of an additional dimension, and because that quantum field theory is conformal, you have the symmetries of an anti-de Sitter space. Now, this looks like a completely shocking equivalence, and I would say that its full implications are far from being understood, but there is a lot of quite non-trivial evidence. People have done many detailed calculations, and somehow so far the equivalence seems to hold true in all the things that people have investigated. So there is a good reason to take it very seriously. And if you apply it to our black hole problem, then as we said, you have a near horizon geometry of some anti-de Sitter 2, and it gives you a very simple statement, generalization of the quantum entropy that we are looking for. That the quantum entropy can be defined as the logarithm of this function W of q in anti-de Sitter space over all the string theory fields with some appropriate boundary conditions and renormalization procedure. And Sen in 2008, he showed that for large charges, the logarithm of W of q reduces to the Bekenstein-Hawking wall formula. So it looks like a reasonable, nice, proper quantum generalization of the Bekenstein-Hawking wall formula. So now can we do something with it? So basically anti-de Sitter 2, if you make a Euclidean continuation, is just a disk with a metric like that, where theta is the angular coordinate and r is the radius, and you have to put some cutoff to make everything well defined, because the volume, this is the Poincaré disk, the volume of this disk diverges. So there is some well defined procedure to get finite quantities answers out of that, and the question then becomes, can we really do something with this, and can we really put this to test? So that's but at least we have a statement that we would like to prove. The statement that, and this is a kind of a summary of what we are trying to do, is that we are trying to show that the Bekenstein-Hawking is somehow related to Boltzmann, because if something has entropy, it must correspond to counting of states, otherwise your understanding of that object is not complete. So this is the quantum generalization of this correspondence, and the quantum generalization is the following, that on the left hand side you have space-time geometry, you just have the geometry of the black hole. On the right hand side, on the other hand, you have a Hilbert space, because you want to be able to count. Just like in our example of a nitrogen gas, on the left hand side you would be doing some experiments by heating the gas in this room, or a black hole on the left hand side. Of course, that's described by space-time geometry, and then the right hand side is the counting problem that you were doing. On the left hand side, therefore, you have a black hole. On the right hand side, you have some soliton, which is called brane in the string theory literature, membrane because of brane, with some charge q. And we have this generalization of quantum entropy defined by some functional integral on IDS2. And then the problem is, can we really check, can we do some check on this theory that in fact this correspondence is correct? So how do we evaluate it? So now, how much time do I have? I have 10 minutes, right? 10 minutes, okay. So now the question that I want to just very quickly go through is, how do you evaluate it? And I don't, for this audience, I don't want to give you too many details, but at least I wanted to give you a flavor that these are quite serious and non-trivial calculations. And if the answers come out to agree at the end of it, there are reasons to take it seriously. So d of q, as I said, so on the left hand side is the d of q, the right hand side is d of q, which is the number of states in the this quantum Hilbert space with some charge, fixed charge q. So you just have to evaluate the dimension of some subspace in this Hilbert space, and w of q is some functional integral whose logarithm is to be interpreted as the entropy. So evaluating d of q is actually an extremely difficult dynamical problem, because it's actually some bound state. This d brane that is responsible for this black hole, this branes, is some complicated solitonic state in the non-perturbative Hilbert space of the theory, and you have to develop clever methods to evaluate this number. And this really work of several people, many groups around the world, including ours, and this problem has been kind of mastered for a class of black holes within string theory. Again, supersymmetric black holes, which means extremal analogues of extremal Reisner-Nordstrom black holes. And w of q is given by some formal functional integral that we need to evaluate. So I just want to illustrate to you by some examples how these things work. So computing d of q, as I said, the problem has been solved, and in some of the simplest examples, there is actually some very beautiful mathematics which enters. And at the end of the day, even though the calculation is very difficult, the answer is specified, is very easy to state. And it is given in many of these examples in terms of Fourier coefficients of some very special mathematical functions called modular forms. So just to make it very concrete for you, here is a definition. So basically a modular form is just a function of complex function defined on the upper half plane, which is very symmetric. But basically it is invariant under SL to Z. These are the transformations under 2 by 2 matrices of integers such that the determinant is 1. So if ABCD is such a matrix, the function has this remarkable symmetry property that's called a modular form. And a simple example of such a modular form, and this number k is called the weight of the modular form. So one of the examples, for example, that the degeneracy depends only on some invariant n, and is basically given by a Fourier expansion of this function. So the function here is the function, it's just 1 upon q product over n, 1 minus q to the n, where q is e to the 2 pi I tau. So tau you can think of as some kind of a chemical potential for n, and now you can put it on a computer and expand it. In terms of q to the n, it's just a Fourier expansion. And then the degeneracy that we are interested in, the physical degeneracy, is related to this number c of n. Okay, so it's a completely simple algorithmic thing that you can do. You can just calculate it, put it on a computer, and you can calculate it. So that's the right hand side of the problem. The left hand side of the problem, so basically what I want you to appreciate is that the calculation gives you some very specific answer. The answer is here, and that's what the theory gives you. On the left hand side, you have to compute the analog of, first of all, you have to evaluate the black hole solution. You have to figure out the generalization of the Kerr-Newman black hole, because here are some additional fields are present. And then you have to evaluate some functional integral in that background. And the first pass is that, okay, you can do that. So it depends on many charges, like 2 or 3 charges. You can take one charge to be large and all other to be finite. And the second pass would be that you take all charges to be finite. And you basically have to use several clever techniques from quantum field theory but just let me give you the results. So in the first case, so this is the analog of a spinning Kerr black hole, Kerr-Newman black hole, with 3 charges in 5 dimensions. And if you evaluate the logarithm of the degeneracy that we computed from some modular form as I gave you, it gives you some non-trivial answer like that. And notice that all these numbers like 3 and 1, so Q3 is large, but Q2, Q1 are all finite. And what you find is that if you calculate log of W from totally different methods using the geometry of these black holes, you get remarkably exactly the same answer, including the 3s and the 1s. So these are really finite size, finite charge corrections. I mean, the point is that we can be sure of our calculational methods to really bet on it that this number is 3 and not 2.1 or something like that. So this gives you some confidence that really something very interesting is going on in the guts of the theory, that the theory somehow knows that the black hole has to have an interpretation as an ensemble of states. Can we do even better? The next question is, what happens if all the charges are finite? That calculation actually turns out to be even harder, but that has also been done through some methods called localization. And what happens is that this functional integral, as you know, functional integral is an infinite dimensional integral over all fields. Using these methods called localization, you basically collapse that functional integral to just it localizes into a finite dimensional integral. In fact, it's some Bessel function, which you can even do. So you get some very nice answer like that. And here is a comparison between the degeneracies that you get. So, okay, so d of the degeneracy depends on only this integer delta, which depends on the charges. And here is the right hand side, 8 minus 12, 39 minus 36, and so on. And here is the left hand side, and you see that you get answers which are very close to the integers. Whereas if you had computed the exponential of the Bekenstein-Hawking entropy, you would be getting answers which are completely way off. So here you see very explicitly that the quantum corrections are really important if you really want to interpret this black hole as an ensemble of states. Moreover, notice that these have alternating signs, and that is because the degeneracies are actually related to this Fourier coefficients with some minus 1 to the delta plus 1, and therefore the degeneracy is strictly positive, as you would expect. So again, this is a prediction from the infrared of the quantum gravity for black holes, which is borne out by the ultraviolet. Now, more interestingly, you might ask, why do we not get a precise integer here? Why don't we get 8? And whereas can we even fix this problem? And it turns out that actually we can, because of the fact that the counting function that I told you is some modular form. There is a famous expansion of it due to going back to Ramanujan, famous number theorist Hardy and Rademacher, which gives you an explicit expansion of this integer, let's say 8, in terms of some Bessel functions. And there are indications, I mean this calculation is not completely finished yet, but basically it seems not unlikely that, it seems very likely that in the near future we will be able to reproduce even precisely this integer. So I think I'm sort of coming to the end of my talk. To summarize, I hope I have given you some flavor. I understand that my talk is perhaps a little bit in a different direction compared to most talks in this conference. And we have heard many very interesting talks about how black holes are, the reality of black holes is being tested experimentally, and there are impressive work on analytical methods, numerical methods, and observational methods. And it has taken us 100 years almost after the Einstein equations were published, and 50 years after this famous solution, and we are still, as we saw, we cannot really assert on the reality of black holes, but I think we are pretty sure that they do exist from the classical point of view. But because of their thermodynamic properties, as we have seen, starting with some robust and well-tested physical principles like thermodynamics and quantum mechanics and general relativity, these black holes continue to inspire us also in our search for a coherent framework for quantum gravity, and in fact they remain one of our most reliable guides, because unless somebody is going to make us a super LHC, this is the best we can do. But string theory does come out of this particular test with, I would say with good, its reputation enhanced a little bit. And what we have learned is that it's an extremely rigid theoretical structure, because all these calculations that I described really depend on the details of the string theory that you're looking at. And if you even change a coefficient in the effective action of string theory, you will get completely wrong answers. And I find it remarkable that gravity, which we all understand, is some kind of is sort of differential geometry. It's geometry. Pushing gravity in the quantum direction, we are able to in fact reproduce an integer, which is a very number theoretic or quantum thing. And as we saw, that some of these calculations actually are capable of reproducing the precise integers corresponding to for which the black hole entropy, the Bekenstein-Hawking formula is just a crude approximation to an integer. As we saw here, for the number 8, the Bekenstein-Hawking entropy would have given you 230, which is a very crude approximation. But now, including these quantum corrections, which we seem to be capable of doing, you can actually hope to reproduce these integers. So I think I'll stop here.